So the next question is, okay, how can we classify critical points? Well, again, we go back to one variable case. Okay, for a function reals into reals, okay, which is differentiable, which is a derivative, okay, I will say not one or two times, I will just say enough times, because it depends on the test. Okay? We have the following. First derivative test. Okay, remember this says that, okay, firstly we have a critical point. So f prime x0 is 0, and f prime changes its sign at x0, it is 0. Okay, here it is positive, here it's negative. That's f prime. It means for f that, okay, at x0 we have a value, but the tangent line is horizontal because it's a critical point. And the derivative is positive, which means function is increasing here and decreasing here. So, of course, local maximum. Okay, this is the first derivative test. Well, if the signs change in the opposite case from negative to positive, you have a local minimum and so on. So this is the first derivative test. Note that it tells something about a direction when x increases. Well, in two variables, we don't have it. And we have no way of generalizing it, because in different directions, there is no increasing concept. So generalizing this is not very practical. In fact, we know that for a functional one variable, this test is not a very useful test either. Instead of this, we used okay, we have the second derivative test. Okay, this said that if f is differentiable enough times, here 2 times, okay, so f has, or f is twice differentiable, and okay, we have a critical point. Okay, then, okay, you recall these things. If f double prime x0 is negative, then f has local maximum. And if this is positive, then f has local minimum. And if the second derivative is 0 as well, because the first one was 0, then no info. So this is what we have from one variable second derivative test. Now we will try to generalize this. Okay. We will state one observation, which actually is correct, but we are not able to prove it directly, but we will again rely on our common sense. The observation is the following. Okay, let f be 2 times, or rather, let me say, let f have continuous second order partial derivatives. Now this says that, first of all, f has a differential because its partial derivatives are once continuous, but even the partial derivatives are differentiable because their derivatives are also continuous. So, okay, f sub x, f sub y are all differentiable. Okay. Then, f has a local maximum at P0 implies, as we already figured out, that in all directions, that is, for every v direction, okay, the curve on top of this direction vertically above this direction, okay, f also has a local maximum. Well, this simply was the observation that if you have a P0 and you have a direction v, you construct the line. On top of this line, okay, you have a surface, okay, but if you just consider this one, okay, say this is the surface, then if you have a horizontal tangent line there, and if it's a local maximum, then this curve also has a local maximum at that point. We already said that. Now, this is true for all directions. So, this implication is correct, obviously. But consider the opposite. Suppose we have a surface and we have a hilltop, something like this. And we intersect it with a vertical plane passing through this point. Of course, we get such a curve. It's a local maximum. Conversely, if for all vertical planes we get a local maximum of the curve, just turn this plane around, you always get a local maximum. So it must be a local maximum for the whole surface. In other words, what I'm trying to say is that if it's true for all such directions, it's an if and only if statement. Now, there's one advantage here, because the right side says something about a curve having a local maximum. Of course, you can state the same thing for a local minimum. For all vertical cuts, the curves you get, if you have always a local minimum, then the whole surface has a local minimum there, because you can rotate them. This is an explanation, not a proof. But it's common sense. We would expect such a result. After all, we assumed f is a very nice function. It has continuous partial derivatives. Okay. Now we know one criterion about the right side, because the right side has something about a plane. We have a vertical plane, and we have a curve, and we have a local maximum. Well, this is guaranteed by the second derivative test if the second derivative is negative there. Okay. So, okay, the right-hand side is guaranteed by second derivative test, okay, of course, in one variable. We don't have one for multivariables yet. So for one variable case, because we have a curve, the right-hand side is guaranteed by the second derivative test if all second derivatives at P0 are negative. Of course, respectively, positive for the minimum case. I'm talking about the local maximum case. So that's what the second derivative test in one variable says. Well, let us look at this more carefully. What is the second derivative of that curve? We know that the first derivative of this curve is the directional derivative, okay, in the direction of v, because the curve is on top of this L, so it must be exactly this. Okay, so, but the derivatives are dv f at P0. So the second derivative is the second directional derivative. And if all these are negative for every v, then we will get indeed what we want. That is a local maximum for the whole surface. So, okay, let us calculate dv of dvf at P0. This is the directional derivative of the directional derivative of f. But here we have differentiability at our aid. So we can assume, first of all, v is cosine alpha sine alpha. For simplicity, take it as a general but unit vector. And okay, since f is differentiable, dvf is gradient f dot cosine alpha sine alpha. Now, using this, I can put here directly this dot product, that is f sub x cosine alpha plus f sub y sine alpha. Everything will be evaluated at P0. But we have another directional derivative to evaluate. Again, we have this the differentiability of both functions, f sub x and f sub y, because we assumed f has continuous second order partial derivatives. So its partials are differentiable. But then this means that we have the derivatives of f sub x cosine alpha plus f sub y sine alpha times, okay, maybe I should write that. Okay, let me explain it in detail to get any confusion. So this is actually the gradient of the function f sub x cosine alpha plus f sub y sine alpha dot this v, which is cosine alpha sine alpha. Okay. This is because this is a differentiable function. And everything will happen at P0. Now, what is that? That's easy to calculate. The derivative with respect to x is then fxx cosine is constant, plus the derivative of fy with respect to x is this one. And we multiply this with cosine alpha. Plus, now the derivative with respect to y of this expression, it is fxy, okay, cosine alpha, plus fyy sine alpha times sine alpha. Now, because of continuity of the second partials, by Clairaut's theorem, fxy and fyx are equal. So this simply says that I have cosine square alpha fxx plus 2 fxy sine alpha cosine alpha plus the last term fyy sine square alpha, all evaluated at p0. Now, let us not forget what we are after. We want this second derivative to be negative for all alphas. And then in any direction, we will have a local maximum. So the surface will have a local maximum. So we want this to be negative for all alpha. That was our goal. Now I will differentiate two cases here. If cosine alpha is 0, then this is, okay, well, what is that? If this is 0, this is 0, it's just fyy sine square pi over 2, because then this must be pi over 2, so it is fyy at p0. Okay. So this is a special case. We will return back to it. Okay, the reason I want to divide by cosine alpha. So let me continue with the expression here. Let me take cosine square alpha out, assuming alpha is not pi over 2, because I will divide. This is then f sub xx plus 2fxy times, okay, dividing by cosine square, you have tangent alpha plus fyy tangent square alpha, all evaluated at p0. Okay. Now I can consider this as my big X, and this is big X squared. So this is P of big X, a second degree polynomial in the variable big X. And for all x, I want this to be negative. So, okay, a polynomial of degree 2, namely P of x, is negative for all x, okay, if and only if two things happen. Just think about a polynomial of degree 2. It is a parabola in plane. Okay. And a parabola will be always negative, means that it will be something like this. Okay. If it intersects the x-axis at one point, it's not always negative. If it's further above, It's even positive at some points. So to guarantee this, first of all, it must not intersect the x-axis. In other words, it will have no roots. So if and only if, okay, it has no roots, but no roots is not enough because, I mean, such a parabola also has no roots. However, okay, I want it to be negative all the time. Well, this is guaranteed if the largest powered term has a negative coefficient. So, and, okay, coefficient of x squared, that is fyy at p0 is negative. So we are almost finished. We can now state our theorem. But before that, I will just summarize what we did. So, conclusion. Okay. If, okay, the polynomial has no roots, but this means the discriminant is negative. And fyy at p0 is negative. Then, okay, the second derivatives are all negative. So, in all directions, okay, we have a local maximum. So, fxy has a local maximum. So, if this is true, then f has a local maximum. This is what we tried to show. Now, what does a discriminant is negative mean? What is the discriminant here? Going back to the polynomial, again, we see that, okay, the discriminant is, of course, b squared minus 4ac. So, discriminant is 4fxy at p0 squared minus fxx at p0, fyy at p0. We want it negative. Okay, so this condition says that this must be bigger than, sort of smaller than this product. Well, actually, notation here. One considers the Hessian, which is the determinant of Fij, ij 1, 2, which simply means F11, F22, F12 squared, which is exactly the opposite of this, okay, at P0. So the theorem says the following. Okay. Let f have second order continuous partial derivatives. And, okay, if the gradient of f at P0 is 0, 0, i.e. a critical point, then one has the following. Okay. One, the Hessian at P0, okay, is positive, and okay, Fyy at P0 is positive, then we have a local minimum at P0. Secondly, actually, we proved the second case. If Hessian at P0 is positive and this is negative at P0, then f has a local maximum at P0. And finally, if Hessian is negative, we didn't consider that yet. If Hessian at P0 is negative, then f has a saddle point at P0. And finally, if Hessian is 0, then no. Okay, let us summarize how we proved this theorem actually. First of all, Hessian is positive means, by the notation above, it means the discriminant is negative, so there are no roots of the polynomial. Well, the leading term is positive. It means the polynomial is always positive, strictly positive. Okay. But the polynomial was the second derivative. So this says the second derivatives in any direction are positive at P0. So you always have a local minimum in all directions, which means f as a function of two variables has a local minimum. Okay, we actually proved the second one. Hessian is positive, so discriminant is negative. So the polynomial has no roots, but the leading term is negative, so polynomial is always negative. And so we have a local maximum because we have it in all directions. Now in the third case, if Hessian is negative, that means the discriminant is positive. Well, if in a polynomial of degree 2 you have a positive discriminant, it means you have two different roots. When you have two different roots, between them, if you have positive values, outside you have negative, or vice versa. Namely, you have both positive and negative values depending on big X, which depends on alpha, the direction. So in some directions, the second derivative is positive. In some directions, it is negative. But then you have a local maximum and a local minimum in different directions. So it's a saddle point. Now 4 says that if Hessian is 0, everything can happen. An explanation, just consider z is f of xy, something like x to the fourth, y to the fourth. P0 is 0, 0. Then, of course, gradient f at P0 is 0, 0, trivially, and Hessian okay, is 0. Okay. Now, what do we have? Well, this function clearly has a minimum value at 0, 0, because it's always positive, except at this point. Okay. And since fxy is always greater than f0, 0, which is 0, okay, f has local minimum at p0. Okay. And just consider now g of xy to be the negative of x to the fourth plus y to the fourth. And this has local maximum at p0. Because it's everywhere negative, except at 0, 0, which is 0, so it's the biggest value. And this says that if the Hessian is 0, it's 0 in both cases, okay, you cannot say anything about the function. Having a local maximum or a local minimum, either can happen. Okay, so this is our second derivative test for functions of two variables. Those who will take linear algebra courses later will see that this is about what is called positive definiteness of the matrix Fij I just mentioned above. You should be careful not to confuse the Hessian and the discriminant. One is the negative of the other. So you should have some practice in that. Okay, a last remark about the theorem. Okay, our arguments also include the case when alpha is pi over 2. Because then fyy will be positive or negative, okay, depending on, of course, the conditions in 1 and 2. So, okay, our arguments at the end, at the statement of the theorem, also include the case alpha pi over 2. Okay, which we had excluded because we wanted to divide by cosine alpha. Okay, and okay, also the condition fx fyy at p0 is positive or negative, okay, is equivalent to saying fxx at p0 is negative, respectively positive, in case, okay, the Hessian, okay, is positive or negative. Okay, this is because of the following. Okay, Hessian, remember, was fxx fyy minus fxy squared. So, okay, if the Hessian is positive, the first case, then fyy negative implies directly that the other one is negative, because for this difference to be positive, this is already negative, this must be positive and larger. So they must have the same sign. In other words, we formulated the theorem for fyy, but it's the same thing if you replace it with fxx, because they have the same sign in 1 and 2. Okay. In the third one, we don't have any problems. We don't care about fyy being positive or negative. Just Hessian is negative. Okay. So it doesn't matter. If one formulates the theorem with fxx at p0 instead of fyy. Next, we will consider some examples.